So let's take this problem. A material is subjected to tensile stress of 125 Newton per mm square in one direction, another tensile stress of 50 Newton per mm square in a direction at right angle to previous stress, and shearing stress of 30 Newton per mm square as shown in figure below. Determine stresses on a plane, the normal to which makes an angle of 45 degree with the stress 125 Newton per mm square. So as in the figure, on one face stress P1 is equal to 125, and another face which is at right angle P2 is 50 Newton per mm square. The shear stress is 30 degree. We have to find normal stress on a plane which is inclined at 45 degree. So the value of normal and tangential stress on an inclined plane are given by Pn is equal to P1 cos square theta plus P2 sin square theta plus Q cos 2 theta, or by transformation equation Pn equal to 1 by 2 P1 plus P2 plus 1 by 2 P1 minus P2 cos 2 theta plus Q sin 2 theta, and Pt is given by 1 by 2 minus of P1 minus P2 sin 2 theta plus Q cos 2 theta. The values here are given, such as P1 is equal to 125 Newton per mm square, P2 is equal to 50 Newton per mm square, and Q is 30 Newton per mm square. The angle of inclination theta is 45, so 2 theta will be equal to 90 degrees. Now calculating the Pn, we have Pn equal to 1 by 2 P1 plus P2, which is 125 plus 50, plus 1 by 2 P1 minus P2, that is 125 minus 50 cos of 90 plus 30 sin of 90. So putting values, we get 175 by 2, that is 87.5, plus 0 since cos 90 is 0, plus 30 as sin 90 is 1, which gives Pn is equal to 117.5 Newton per mm square. Since it is positive, it will be tensile in nature. Now calculating value of Pt. Pt is equal to minus 1 by 2 P1 minus P2, that is 125 minus 50 sin 90 plus 30 cos 90. So that gives us minus 1 by 2 into 125 minus 50, that is 75, into 1 as sin 90 is 1, plus 0 since cos 90 is 0. So this gives a value minus 37.5 Newton per mm square. The negative sign shows that the direction of Pt is opposite of the one shown in the figure. Now the resultant of the Pn and Pt, Pr will be equal to root Pn square plus Pt square, that gives equal to root of 117.5 square plus minus 37.5 square. Solving this, will get a value equal to 123.4 Newton per mm square. So resultant stress of Pn and Pt is 123.4 Newton per mm square. The angle which the resultant Pr makes with the Pn is given by psi equal to tan inverse PT by Pn, that is tan inverse minus 37.5 upon 117.5. This will give a value of psi which will be equal to minus 17.7 degrees. So the negative sign shows the angle is in clockwise direction. So resultant will be in a clockwise direction from the Pn. So if Pn is in this direction, the angle 17.7 has to be measured in clockwise direction like this. So now what we have obtained so far is, we'll show on diagram the values we have obtained. Pn, the normal stress on the inclined plane, is shown like this, which makes 45 degrees from the direction of stress 125 Newton per mm square, and the stress is shown in this direction PT. So on the other face the direction of shear stress will be like this, and similarly on other faces the tangential or shear stress will be like this. Pn is equal to 117.5 Newton per mm square. Pt is equal to minus 37.5 Newton per mm square. All the shear stresses will be of the same magnitude. The direction will differ as shown in the figure. Now the resultant of Pn and Pt will be like this. Pn is equal to 117.5 in this direction, Pt in this direction, and resultant is equal to 123.4 Newton per mm square at an angle 17.7 degrees from the Pn as shown in the figure. Now what is remaining is the normal stress on the other face, which is at an right angle. From the corollary we know that Pn plus Pn dash will be equal to P1 plus P2. So Pn dash will be equal to P1 plus P2 minus Pn, that is 125 plus 50 minus 117.5, which gives a value 57.5 Newton per mm square. Now let us solve this problem graphically. So graphical solution is also called Mohr circle solution. Let us recall the values. P1 is equal to 125 Newton per mm square, P2 is 50 Newton per mm square, and Q is 30 Newton per mm square, and theta is 45 degrees. Let us draw a line from the origin OA, which is in magnitude equal to the stress P1, that is 125 Newton per mm square. Similarly, from the same origin, let us draw a line OB, which represents the other normal stress, that is 50 Newton per mm square. Since both are tensile, they are measured in the same direction. From the point A, since the shear stress is positive, draw a line perpendicular to the value of shear stress, that is 30 downward, and from point B upward and if we meet these 2 points, the line will pass from the midpoint of the line AB. Now let us say the center is C. From this center, either with a radius CZ or CF, any of the radius, let us draw a circle like this, which passes through point F and G, the points representing the shear stresses with sign conventions. Now let us draw a line which is at 2 theta from the line CZ, right? This angle is 90 degree, that is 2 into 45. Since the angle of inclination is 45, let us say this point is D. Now we will drop a perpendicular from D on the line OA, which is the x-axis, and let us say the point is E. Now OD represents the resultant stress PR. So let us join the points O and D. Now PN is given by OE and PT is given by DE. So OE is 170.5 and PT is equal to 37. Let us measure it. DE is 37. And the angle psi, which the resultant makes with the stress Pn, is DOE. So let us measure the angle DOE, which is psi, which comes to be 18 degrees, which is very close to our numerical solution 17.7. There are sign conventions of the Mohr's diagram. A positive shear stress is drawn below the line OA, that is x-axis. The resultant stress PR is measured by OD, and which comes to 124, which also is very close to the value obtained by numerical